अच्छा order 2 के बारे में what we did was कि I told you कि so I'm just going to repeat one small mechanism, which is that, for example, if I have वही वाला question कर लेते हैं कि I had 2NO and they were reacting with Br2 and together they were producing 2 molecules of NOBr. That was the reaction, and the mechanism was that it had 2 steps. The NO went on to react with Br2, and when it did, it would produce. It's going to produce NOBr and a bromine atom or radical. And then in the next step, another NO will come in, and it will react with the bromine atom, and it will produce the second NOBr. ठीक है, ये मैंने कल किया था, and we said कि let's say that's the mechanism of the reaction, and I explained to you that when this happens, as I explained to you when this happens, let's say the second step is the slow step, and the first step is your fast step. So होता ये कि the second step being the slow step, the rate depends on your two reactants that are involved in the slow step. So the rate of the reaction is first order with respect to NO's concentration and it's first order with respect to the Br atom concentration. ठीक है, ये हमने discuss किया था. But then I told you that the Br over here is actually an intermediate. It's not actually produced, it wasn't a reactant, it's actually produced while the reaction is happening. So that thing over here is my intermediate. And this Br is produced when Br2 and NO react. So the concentration of this Br actually depends on the concentration of Br2 and NO. If their concentration is high, the amount of Br produced will also have a higher concentration. So when I say that the reaction is dependent on the Br atoms, it's actually indirectly dependent on the NO concentration and the Br2 molecule concentration. Because the Br atoms were actually produced in the previous step. So these two reacted, and when these two reacted, they ended up producing this Br atom over here. So the Br concentration actually depends on these two. And then when I looked at my rate equation, what happened was, after I did this, when I look at my rate equation, it looks like this. It's rate is dependent on NO concentration squared. And on Br2, it's only dependent on once or directly proportional. So with NO, it's a quadratic relationship. This is what we learned yesterday. So with NO, it's a quadratic relationship. Why? Because if you increase the concentration of NO, lets you double the concentration of NO, the reaction speeds up. But because of NO's concentration, the amount of Br atoms that are produced also double. So the reaction speeds up again. So it's a quadratic relation that the reaction, by just doubling the concentration of NO, not only does the reaction speed doubles because of NO, but because of NO, the Br atom also increases. So its concentration also doubles and the reaction speeds up once more. So that's a quadratic relationship. You double NO's concentration, the rate increases 4 times because it's doubled twice. But if you, with Br2, it's order 1. So if you increase concentration of Br2, the reaction speeds up. Why? Because increasing the concentration of Br2 increases the concentration of Br atoms. So only one of the reagents in the slow step actually speeds up. So the reaction only speeds up once. It doesn't increase 2 times. So that's why it's order 2 with respect to NO and just order 1 with respect to Br2. So that is, remember, that's one way of figuring out the order of a reaction. Okay, remember this. Okay, I'll just sum this up. Remember this, that the rate of the reaction depends on the slow step. Any reactant or intermediate that's involved in the slow step, the rate of the reaction depends on those things. So it depends on NO and Br. But since Br is an intermediate, that intermediate itself is dependent on Br2 and NO. It depends on these two things because they make Br. So when I say that rate depends on Br atom, it actually indirectly depends on Br2 and NO. So the rate of the reaction depends on these two things. And if I sum this up, I'm going to get order 2 with respect to NO. Okay, but is this all clear? The mechanism part? Clear as far as business clear? Isha. So one second. So the thing is, so we're going to move. So this is number one, the first way of finding the order of a reaction. Now, what I'm going to do is let's try and figure out another way of finding out the order of a reaction. The other way is by plotting a graph. Okay, by plotting or by doing an experiment. So what's the other way of finding? So the second method of finding order. That's a second method, and that's this method over here. That's known as the half-life method. So that's my half-life method. Okay, that's like radioactive decay. I mean, you had half-lives and radioactive decay. So what is this? What is this method? And what happens in this method? So let's say I've got a reactant. There's a reaction that's happening. X reacts and it produces or ends up producing Y. So there's only one reactant, and that reactant is X. So the rate of the reaction depends on the concentration of X. So we don't know what the mechanism is. Let's assume, I mean, because remember, when we see a reaction happening, most of the time we don't know what the mechanism is. So I know that, let's say I know that rate depends on, I mean, my assumption is that the rate depends on the concentration of X, right? Maybe it does, maybe it doesn't. I have no idea because I don't know what is the mechanism of this particular reaction. I don't know what happens. Does X react with something else first and then something happens and then Y is produced? I have no idea what is the process of this reaction. So there's a question mark. I have no idea how the rate is dependent on X, the concentration of X. I said, but one thing is for sure that when the reaction happens, what happens to the concentration of X is it decreases, right? So whenever this reaction happens, I mean, whenever any reaction happens, the reactant concentration decreases with time. As I said, it continuously decreases with respect to time. Now, since it is decreasing, how would the order? Because remember, we don't know what the order is. So let's say the order is 0. So order is 0. What kind of graph would I expect? How will the concentration of X decrease with respect to time? Now remember, this is a different graph than the ones that we did previously. So this is time. This is the concentration of X with respect to time. Now, and I'm saying that it's order zero. Order zero means that the reactant concentration will decrease. It's going to be very high at the beginning, and then it's going to decrease with respect to time. Like if you're burning a match, right? What happens to the match? It slowly gets used up. There's less and less match left at the end. So the reactant kind of gets used up. You burn paper, the paper eventually finishes. If you pour a can of fizzy drink in a glass of water, slowly all the bubbles they will form, and the carbonate that is dissolved in the fizzy drink, it's going to go to zero, right? So the concentration of X will decrease, and the reactant should go to zero over time because it's all going to get used up. Now, if it's order zero, the graph would be kind of like this. Remember, I told you that the gradient is the speed of the reaction. The gradient of the concentration time graph, or how the concentration changes with respect to time, that is the rate of the reaction or the speed of the reaction. Now, what is happening is that in this case, it's constant. That means the reactant gets used up. The reaction or the speed with which the reaction is happening is unchanged. Order zero ka hi matlab hai na, if it's something is order zero, that means there will be no effect whatsoever on the rate of the reaction, no matter what happens. Okay, so if you're burning a piece of paper, the speed with which it was burning right at the beginning, it's going to be the same speed at which it will be burning right at the end. So the concentration of X will decrease at a constant pace. The rate of the reaction will remain unaffected by the concentration of X. So is this part clear? John, is this clear? Aseeb, John, is this clear? And remember this, that most reactions, as I remember this, most reactions don't actually follow this. It's they always slow down. Like if you burn a piece of match or a matchstick, what will happen is that the flame will start to die off. The reaction will become slower and slower over time. So the gradient actually becomes slower. It becomes less steep. It takes longer and longer. The reaction, like if you pour a piece of if you pour fizzy drinks in a glass of water, initially there's a lot of bubbles produced, but the bubbles they slowly die off. But the speed with which the bubbles are forming, that kind of decreases. It's taking longer and longer. So in zero order, the reaction will be constant. It's going to just happen at the same speed. Most reactions are not actually order zero. So what if it had been order one? What would the graph look like if it had been order one? So I'm going to sketch an order one graph. So order one, what will happen is that the rate. One second. So the same thing, but now the relationship is. So now the relationship is going to be order one. One second. You fizzy drinks wala na. I'm just saying that like if you pour a can of Pepsi in a glass of water, right? So there's a reaction happening. You see bubbles of gas coming out, right? Initially, the reaction is fast, and then it slows down. It becomes slower and slower. So I was saying that most reactions, the speed does not remain constant. It's always faster in the beginning, and it's slower at the end, right? Most reactions. So most reactions are not actually order zero. Order zero means that the reactant is going to be consumed at a constant speed. That usually does not happen. In normal cases, it's always the reaction is faster in the beginning and it's slower at the end. Okay. So most reactions are actually kind of close to order one. So what would an order one graph look like? So order one means that the rate of the reaction is dependent on the concentration of the reactant. Okay, X is my reactant. Okay, that's power 1. That means if X gets used up, the reaction will slow down. If X gets used up even more, the reaction will slow down even more. It's a direct proportionality. Okay? So the more of X gets consumed, the slower is the reaction, because there'll be less frequent collisions. Okay? Most reactions actually kind of are faster in the beginning because the reactant concentrations are very high at the beginning, and then they start to slow down. So the graph of a first order reaction, it's not going to be a constant straight line. It's not going to be a line even. It's going to be something like this. So let me plot this. That's let me count the box. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. I said most reactions will have a graph that would be very similar. I said let me just plot the points. First, it's this one, then it's so most graphs, they would kind of follow this pattern. It's going to be kind of a curve. So most graphs would actually look like this. What's happening is that as the concentration of X decreases, the reaction is very steep at the beginning. It's fast in the beginning, but as the concentration decreases, the reaction is slowing down. It's going to take a longer and longer time for the reaction to finish. Okay, right at the end. So you must have noticed that fizzy drink glass that will have the rate at which the bubbles are getting produced, that's going to become slower and slower. It's going to take a longer and longer time for the reaction to actually go to completion. It never actually goes to completion because if the concentration of X continues to decrease, the particles of X, they decrease, there'll be fewer and fewer collisions, and the time taken for the reaction to happen is going to be longer and longer. This, I mean, if I just visually state that, it's going to look like this. Okay, right in the beginning, there's a lot of reactants, right? So they're having a lot of collisions right at the beginning. It's a very fast reaction. So there's a lot of X and all of them are colliding, and then slowly, with time, the concentration of X decreases. It gets used up. And now you're going to have fewer collisions. After some time, some more of X will react, right? Now you're going to have even fewer collisions. Then after some time, the concentration of X decreases further and the particles are like flying around, but they can't find each other. So there'll be even less frequent collisions. The concentration of X decreases further and you'll have even less frequent collisions. It's going to take a longer time. How you order 1? I mean, this is X to the power 1. This is order 1. Okay, so is this graph clear? Then what would an order 1 graph look like? And let me the gradient, which is basically equal to the rate of the reaction. Remember, the steepness of the change is the rate. It decreases. The reaction slows down as X gets used up. it slows down as X gets used up. So we've done. So if I plot the reactant concentration, I'm going to get two graphs. I'm going to get a graph of order 0. That means no matter what happens, as the reactant gets used up, there's absolutely no effect on the speed of the reaction. The speed with which the reactant is getting used up, it remains constant. But over here, the speed is faster in the beginning, but then it starts to slow down. It takes a longer and longer time for the reaction to finish because the concentration continuously decreases. Okay. So are these two graphs clear? These two. Clear है ये दोनों? Shahan, Haseeb, Umar, is this clear? अच्छा, so order 2 पे आ जाते हैं. What would the graph of order 2 look like if the rate of the reaction dependent on the reactant and it's got a quadratic relationship? So that is order 2. Okay, so what happens if it's order 2? So that means the rate actually depends too much on the reactant concentration. X being my reactant, and it's got a squared relationship. So what will happen in this case is that if the reactant gets used up, the rate will slow down not proportionally but by a much bigger amount. It's going to slow down too much. It's like if during the reaction the concentration of X decreases by half, the rate will decrease by 1/4. It's a quadratic relationship. If the concentration of X decreases by 1/4, the rate will become 1/8. So the reaction will be slowing down too quickly. It's going to be the rate of the reaction will actually be slowing down a lot faster. X getting used up, the rate slows down, but not proportionally, but by a much bigger factor. अगर ये half होता है, this will become 1/4. So the graph of an order 2 reaction, if you plot the reactant concentration with respect to time, it's going to be something like this. So it's going to be something like this. Okay, so 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So starting at this point, that's the concentration of X. And this is what it would look like. It's then as it's just anyway, so the graph would kind of look like this, which is kind of similar to how the graph actually looked like for the previous one. I'd say it's kind of like this. So this is kind of similar to this graph, but the reaction is actually slowing down, and the time taken, it continues to increase by a much bigger margin. Okay, because every time the concentration decreases, the rate does not decrease proportionally, it decreases by a much bigger amount. Concentration decreases to half, rate decreases by 1/4. So it takes a much longer time every time. So now how do you figure out which graph is which one? There's a concept called the half-life, which is that half-life is the time that is required for the concentration to decrease by half. Radioactive decay, and then you had this concept. So half-life is this thing that this is the time that it took for the concentration of the reactant to decrease by half, right? So it took this much time. The second half-life will be that this is the time that is required for the concentration to decrease by half once more. So basically that's 1/4. Half of half is 1/4. This is the time required for the concentration to decrease by half once more. Okay, so half of 1/4 is 1/8, right? As anyway, so this is basically that if the concentration was 1 initially, half the karne ke liye it required this much time, and that's let's call that t. Let's 1 second. So let's call this one जो पहला वाला है. So this is the first half-life. I'm going to call it T1. This is the second half-life. Like once it became half, the next half, what time did it take for the reactant concentration to decrease by half once more? I mean, from here to half again, this is the time that's required. So it's so that one is going to be T2. And this will be T3. That's the third half-life. Okay, so one thing that you'll notice is that every time the half-life is decreasing, it's decreasing by a factor of 2. I mean, if this took 10 seconds, this would be 5 seconds, this would be 2.5 seconds. So every time the reactant concentration decreases by half, the time required also decreases by half. Pehli dafa it took 10 seconds, second time it took 5 seconds, the third time it took 2.5 seconds. It's I mean, if you can just look at the schedule, you'll get the idea. So is this clear? Do you understand what half-life is? I mean, this is the first time it got half, then half of the previous half, that's 1/4. Then again half, that's 1/8. So is this clear? Anna, Alicia, is this clear? So every successive half-life is half of the previous half-life. Every successive half-life is T3 starts at this point. Okay. I mean, this is T3. Like this, from this, T is equal to 0 to this point over here. That's the first half-life. That's the time that's required for the concentration to decrease by half. I mean, this was your starting concentration, right? So it took this much time for the concentration to decrease by half. That's T1. What's after that? That's T2. I mean, this is your starting point. How much time did it take for the concentration to decrease by half once more? So it's this point, this line over here. You clear it? Just 1 second. I said, what about over here? What's the half-life situation in order 1? Remember, the reaction is slowing down. The rate depends on the concentration of X. If X gets used up, the reaction slows down. And it slows down proportionally. Now, in this case, the half-life is going to be constant. Like if I were to sketch, that's the time required for the first half-life, right? Then I said that's the time that's required for the second half-life. and you can kind of notice that all these half-lives, they are coming out to be exactly every time it's exactly the same. Yeah, that's the time required for the concentration to decrease by half. That's the time to decrease the concentration by half once more. That's the third half-life. That's the fourth one. So that's the first half-life. That's the second one. That's the third one. That's the fourth one. So all of them are exactly the same. Every time the reactant takes exactly the same time for its concentration to decrease capillary and it decreases to half. That's over here. Then it decreases by half once more. That's the time required. Then it decreases by half once more. That's the time. It decreases by half once more. That's the time required. So all half-lives are constant. And finally, the third one, where it's order 2, that means if the concentration of X decreases, the reaction slows down by a much bigger amount. So it takes a much longer time for the reaction to actually finish. In this case, the half-life doubles every time. The first half-life, the second half-life is going to be double of the previous half-life. The third one is going to be double of the previous half-life. The reaction is taking a much longer time every time. If you've got, this is the first half-life, this is the second half-life, and this over here is the third half-life. So each successive half-life is double the previous half-life. It just takes a much longer time for the concentration to decrease because it's slowing down a lot more. अगर ये half होता है, this would become 1/4. So it slows down by a much bigger amount. So each successive half-life is double the previous half-life. The previous half-life. Okay, is this clear? So by just looking at the reactant graph and how does the reactant concentration vary with respect to time? You can just plot the graph and you can measure the half-life. If it's a straight line, that's order 0. If it's a constant half-life, that's order 1. If it's the time is doubling every time, that means it's order 2. Okay, is this clear? ये clear है सारों को? So if it's Umar, is this clear? Anna? So Basim, Shan. So here, just remember this is method number 2. So it's a very simple topic. It's you just look at plot the reactant concentration, and you can, by just looking at the shape of the graph or the half-life, you can just figure out what the order is for that particular reactant. All you have to do is you have to plot the reactant concentration. Or pehla wala tha, that was that you can do that by using mechanism of a reaction. So you can either, if you know the mechanism, you can use the mechanism, or you can just do an experiment and plot how the concentration changes with respect to time. That will give you an idea of what the half-life is and what the order is. So we'll do the third method. That's the final method of finding the order of a reaction. Let's do that tomorrow then. Yeah. Okay, everyone. Office.